All right, so let's do section 1-2 in trigonometry, starting on page 128, talking about angle relationships and similar triangles. So we're actually going to be going over some geometry constructs here, but we will be using them in trigonometry as we move throughout the course. All right, so first of all, we have the definition of vertical angles. Vertical angles are the angles that are created when two lines intersect. And they are non-contiguous. So these two angles are considered vertical angles because they are created by the intersection of two lines. And vertical angles are always the same measure. By the way, these two angles are also vertical angles, and they are also the same measure. The number of loops is a mechanism used to show angles that are the same measure. So see how this has one loop? So any other angle in the diagram that has a single loop, they would be the same measure. So vertical angles are always the same measure. We like that truth. And then we also have, if you have parallel lines, these two lines are parallel, they will never intersect, and they are cut by a third line. These two parallel lines are cut by, this would be called a transversal. Parallel lines cut by a transversal create all sorts of angle relationships. Okay, so if we look at this intersection point, we have a above to the left, meaning above from the intersection. We have above the intersection to the right. We have below the intersection to the left, and we have below the intersection to the right. So angles that are created with parallel lines cut by a transversal, these two angles would be considered corresponding angles. They're both in the same position. They are both above and to the right of the intersection point. Corresponding angles are always the same measure. Well, of course, vertical angles are always the same measure. So if this angle has a certain measurement, then so does this one. And then so would this one, because these two are corresponding. They are both below and to the left of the intersection point. So when you have two parallel lines cut by a transversal, the vertical angles have the same measure. The corresponding, meaning corresponding position, the corresponding angles have the same measure. All right, if we look at this transversal here, the transversal is the line that is not parallel. The space inside the parallel line is called the interior. See these two angles? They are on different sides of the transversal. We would call those alternate interior angles. Alternate interior angles also have the same measure. So this angle has the same measure as this angle because they're both inside the parallel lines and they're on opposite sides of the transversal. Those are alternate interior. And then as you can see, there's all sorts of relationships that are created. Alternate interior angles are equal. Also, the area outside the parallel lines, called the exterior. Alternate, meaning on two different sides of the transversal, exterior angles are also the same measure. So outside the parallel lines, this angle is on the right of the transversal, and this angle is on the left of the transversal. So those are also the same measure. Okay, so corresponding alternate interior, alternate exterior, vertical angles all have the same measure. Of course, since these are straight lines, this angle and this angle are supplementary. Go to the lower right, that means that these two angles are supplementary and these two angles are supplementary. Because of the vertical angles, these two angles are supplementary. So when you have parallel lines cut by a transversal, you can think of it this way, unless they're absolute right angles. There is a large angle that's created, and they are all same measure as each other. And there's a small angle that's created, and they are all the same measure as each other. All right, so how are we going to use this? Talking about angle measures. Let's look at example 1 on page 129. All right, so here I have two parallel lines, and they're going to be cut by this transversal here. And rather than naming the angles with letters, we can also name them with numbers. So this would be considered angle 1, angle 2, here's angle 3, and here's angle 4. And we're told that angle 1 is 3x plus 2 degrees. And we're told that angle 5 is 5x minus 40 degrees. And we want to find the measure of angle 1, angle 2, angle 3, and angle 4. Well, the measure of angle 1 is going to equal the measure of angle 4 because they are alternate exterior angles. So that's going to tell me that 3x plus 2 is going to equal 5x minus 40. All right, so we'll subtract 3x from both sides, and we get 2 equals 2x minus 40. And then we'll add 40 to each side. So we'll get 42 equals 2x, and since we want to solve for x, we get x is equal to 21. Now that's not my answer. I'm going to use that to find my answer. So the measure of angle 1 is going to be 3 times 21 plus 2. So the measure of angle 1 is going to be 65 degrees. Well, if the measure of angle 1 is 65 degrees, because 1 and 3 are vertical, the measure of angle 3 is also going to be 65 degrees. And since 1 and 4 are the same measure, or you can even say since 3 and 4 are the same measure, the measure of angle 4 is also going to be 65 degrees. If we wanted to do a check, we could do 5 times 21 and subtract 40. We would get 65. So that leaves us to try to find the measure of angle 2. Well, angle 2 is supplementary, creates a straight line with angle 1. Or you could say 2 is supplementary to 3. Supplementary to both of them. So supplementary means the sum equals 180. So 180 minus 65 is going to be the measure of angle 2. 180 minus 65 is 115 degrees. So we have the measure of angle 1, the measure of angle 2, the measure of angle 3, and the measure of angle 4. And we found that as parallel lines are cut by a transversal. Some other properties of triangles, or some other properties that we're going to use in trigonometry, is the property of a triangle that the sum or the total of all 3 angles will always equal 180 degrees for a triangle. So if the sum of all the angles of a triangle will always equal 180 degrees, let's look at example 2 on page 130. In example 2, we have a triangle here. You always have to read the diagram. You can't make any assumptions that just because the angles look equal does not mean that they are equal. So here, this is a 48-degree angle, and this is a 61-degree angle. And we want to find the measure of angle X. All right, so that would mean X plus 48 plus 61 is going to equal 180. 48 plus 61 is 109. So X plus 109 would be 180. Let's subtract 109 from both sides. And that will leave us with X being a 71-degree angle. So our third angle would measure 71 degrees. Now the sum of all the angles of a triangle will always equal 180 degrees. But triangles do fall into different categories. They have different types of names. First of all, the type of a triangle, or the name for the type of triangle, can be based on the angles. If all three angles are less than 90 degrees, that would be called an acute triangle. If one of the angles is a 90-degree angle, and we would mark that with our box, that would be called a right triangle. And if one of the angles is greater than 180 degrees, this would be called an obtuse triangle. It's all acute angles, one right angle, one obtuse angle, obtuse meaning greater than 90-degree measure. So a triangle can be categorized by its angles. It can also be categorized by what its sides look like. And by its side measurements. And just as with angles, the number of loops is the way a diagram designates equal measure. The number of ticks on a side denote equal measure. So all three sides here have a single tick. We would call this equilateral. This is an equilateral triangle. Equi meaning equal, lateral meaning side. All three sides have the same measure. If just two of the sides have the same measure, okay, so this side has a single tick and this side has a single tick, that tells me that these two sides have the same measure. I don't even have to mark this one, but if I do want to mark it, I'm going to give it 2 ticks because it's not the same measure of the other two sides. This is called an isosceles triangle. A triangle that has two sides of equal measure is called isosceles. And then a triangle where none of the sides are the same length. I wouldn't even mark them, but if I did want to mark them, I would say this has a measure, this is a different measure, and this is the third measure. None of the sides are equal measure. That is called a scalene triangle. So you can name your triangles based on the angles or the sides. So we could actually call this an equilateral acute triangle. We would call this an isosceles acute triangle. We would call this, with these two sides being equal, a right isosceles triangle. So you can give it its name based on its angles and its sides. All right, some other notations that we use, that we pull from geometry, that we use in trigonometry are similar, S-I-M-I-L-A-R, similar. Similar means same shape. Two triangles are similar, they are the same shape. Congruent means same shape and size. The symbol for similar is like a tilde. That means two triangles or two angles are the same shape. Congruent means same shape and size. So let me give you an example. These two triangles would be considered similar if this angle equals this angle, and this angle equals this angle, and this angle has the same measure as that angle. They're the same shape, but they're obviously not the same size. Their sides are in proportion to each other, but their sides are not equal to each other. Congruent would be same shape and exact same size. This angle equals that angle. This angle has the same measure as that angle. This angle has the same measure as that angle. And this side has the same measure as that side. The sides have the same measure as well. So that's the difference between similar and congruent. And hopefully you're getting used to the tick marks to show angle measurements and the arcs to show angle measurements and the tick marks to show side measurements. So corresponding angles have the same measure. See the single loop and the single loop, those would be considered corresponding angles. See the side between the single loop and the right measurement, the single loop and the side measurement, those two sides would be considered corresponding sides. So the angles are always the same measure. For similar triangles, the sides are proportional. All right, so let's move on to example 3, and we'll use our new definitions of similar and congruent here. Example 3 on page 131, here we're going to have two triangles. We're told triangles ABC and NMP are similar. So here's A, C, B. Here's N, P, F. Single loop, single loop. I'm marking the correspondence. Two loops, and then three loops. So A corresponds to N. Angle C corresponds to angle P. And here we want to find all the unknown angle measures. Well, we're told that angle A is 45 degrees. Well, that must mean the measure of angle N is also 45 degrees. We have A, B, C, N, N, P. Single loop, double loop, triple loop. Sorry, the diagram was off the screen there. So if angle A is 45 degrees, angle N must also be 45 degrees. If angle P is 104 degrees, that must mean the measure of angle C is also 104 degrees because they're corresponding. And the measure of angle B and the measure of angle M are going to be equal. Well, since the sum of all the angles in a triangle will always be 180, we'll say the measure of angle B plus 104 plus 45 has to equal 180. So the measure of angle B, 104 and 45 is 149. Let's subtract 149 from both sides. So we get the measure of angle B is 31 degrees. And you know what? If B is 31 degrees, that must mean N is also 31 degrees because they are corresponding angles. Let's look at example 4 on page 132. Here we have triangle ABC and triangle DEF are similar. Same shape, but not the exact same size. A, C, D. And we'll try to draw a similar triangle here. D, E, F. A and D are corresponding. C and E are corresponding. And B and F are corresponding. And what we're told is that in this larger triangle here, the measure of this side is 24. Measure of side AC is 16. The measure of side CB is 32. And ED is 8. So we want to find the other two sides of this smaller, similar triangle. The sides are not equal, but they are proportional, which means I always write which triangle I'm looking at. The large one is on the top and the small one is on the bottom. You can put the small one on top and the large one on the bottom too. The idea is to not get your numerator and your denominator mixed up. So we know that side 16 is proportional to 8. That's the same as side of length 32 is proportional to, that's considered side that goes from E to F. 16 to 8 is the same as 32 to EF. And we could probably do this mentally, but let's remember when you have two fractions with an equal sign in the middle, you can cross multiply. 3 times 32 is going to equal 16 times EF. Okay, so 8 times 32 equals 256 equals 16 times EF. And if we want to get EF by itself, we're going to divide by 16. We get 16. So the length of side EF is 16. We're going to do the same thing for side DF. We're going to say 24 is to side DF as 16 is to side 8. My large measurements are in the numerator. My small measurements are in the denominator. And let's cross multiply. 16 times side length of DF is going to equal 8 times 24. So that means 16 times side DF is going to equal 192. To get side DF by itself, we're going to divide by 16. We're going to get side DF is equal to 12. So these are similar triangles. And then last, let's look at example 5. We're going to use the concept, or use what we know about similar triangles. It says workers must measure the height of a building flagpole. Okay, so this flagpole is pretty big. Must be pretty big if the firemen can't figure out how tall it is. Okay, they find that the instant when the shadow of a building that is 18, the instant when the shadow of the building is 8 feet long. Okay, so here we have a building, and the sun is over here, and the shadow cast by the building is 18 feet. And this is a 10-foot building. Okay, so here's my shadow, and I know that this is a 10-foot building. That's actually creating a triangle And since buildings are stand right out of the ground vertically, so it's a 90-degree angle there, I have a right triangle. One leg is 10, the other leg is 18. They say at that exact same moment when this building's shadow is 18 feet long, the shadow of the flagpole, so here's my flagpole, is 27 feet long. Well, shadows are created by the angle of the sun. And so that must mean that these two triangles are similar, which means the height of the flagpole, so we'll call that H. The height of the flagpole corresponds to 10, where the shadow of the flagpole corresponds to 18. But if your correspondence, and we want to try to find H, so let's cross multiply. 18 times H is going to equal 27 times 10, or 18H is going to equal 270. To get height by itself, divide by 18, and 270 divided by 18 is 15 feet. This is 10 feet high, casting an 18-foot shadow. This flagpole is going to be 15 feet high, casting a 27-foot shadow.